you have a clicker? It's this. Okay. Hi, everyone. Thank you for coming. My name is Guillaume Beaulieu. I'm a PhD student at the École Polytechnique Fédérale de Lausanne in the Hybrid Quantum Circuit Lab. And today I'll be introducing our recent results on the observation of dissipative phase transitions in a two-photon driven Kerr resonator. So let me begin by briefly introducing what are dissipative phase transitions and why we're interested in them. So dissipative phase transitions are different than the more common thermal and quantum phase transition. They typically occur in open quantum system, which can interact with their environment through the presence of drive and dissipation. And in this case, it's the interplay, the competition between these three different terms, the drive, the Hamiltonian, and the dissipation that give rise to different phases and transition between them. So the first reason why we care about these transitions is that it's interesting fundamental physics. They occur in any type of open quantum system and can always be described by the same formalism. So they've already been observed in atomic system, polariton, circuit QED, and optoelectromechanics. We're mainly interested in the circuit QED platform. The second reason is that they can be exploited to achieve some technological advantage. Some applications are the engineering of robust CAD qubits and to achieve some enhanced metrology by using critical points, for example, to perform better qubit readout. Okay, but before pursuing these applications, we thought that the first thing that we should do is to get a deeper understanding of these transitions, to find a good model that describes them, and actually show that this model reproduces the experiment. And this is what I'll be presenting today. So the model that we're considering is a cavity that has a certain nonlinearity U and is subject to a two-photon drive G. It also has some single photon dissipation rate kappa and some two-photon dissipation rate eta. And in practice, this is how it's implemented. So the main component of this experimental setup is a superconducting circuit, which is made of a λ/4 resonator and is terminated by a squid, which makes it nonlinear. And then on the other side, it's coupled to a feed line, which allows us to extract the number of photons and the two quadrature of the signal. And then the two-photon drive is realized with a nearby inductance, which we use to modulate the flux in the squid at around twice the resonance frequency. So we're effectively parametrically driving the system. Okay, so the first measurement that we perform is to get the number of photons in the steady state as a function of the cavity to pump detuning and for different two-photon drive power. And from this, we took some cuts and we applied a certain rescaling. And this rescaling is simply dividing the detuning and the number of photons by a scaling parameter L. And the scaling parameter is nothing else than a multiplication factor on the pump amplitude. And why do we do this? Is because the theory has shown that we can, that as we increase the scaling parameter L, the system goes more and more towards the thermodynamic limit. So it's a way to implement an effective thermodynamic limit in our finite component systems. And then as we increase this L, we should see that the transitions become sharper and the effect associated with it clearer. So here you have the dots, which are the experimental points, and then the solid lines are the theory fit. And in this rescale picture, we have that depending on the detuning, we can observe different phases. So at the most negative detuning, we have the vacuum. And then as we increase the detuning, this vacuum starts to elongate, and then it separates into two, a plus alpha and a minus alpha state, which we call the bright phase. And if we increase a little bit more, we have both the bright phase and the vacuum before going back again to the vacuum. So if you're a bit familiar with dissipative phase transitions and your eye is a bit trained, you can already see some clear signatures of two types of transition. So a first order DPT and a second order DPT. And it's one of the reasons which makes this device so interesting is that you have both types of transitions all within the same system. So what I'm going to talk about next are these two regions that we're interested in and see what the model predicts. So for the first order DPT, the model predicts that we should observe B-stability at the transition, which means that we should see both the vacuum and the bright phase in an equal mixture. And we should have a metastable region all around the transition. And we also expect to see some critical slowing down, which in this case means that the lifetime of this metastable state will become longer as we go closer to the transition and as we scale toward the thermodynamic limit. So we went ahead and looked for the signature in the experiment. So again, this is the number of photons as a function of the detuning. And if we look exactly at the point of the transition, we have an equal mixture of the bright phase and of the vacuum. But if we detune a little bit to the left, we have that the bright phase is more probable, and a little bit to the right, the vacuum is more probable. So this defines our B-stability region. And then we expect to see some metastable vacuum on the left. And this can be seen in the experiment. So what we do is that we turn the pump on at t is equal to 0, and then the system will stay in the vacuum for a certain time. So this is shown by the red trajectory here. So at t is equal to 0, we turn the pump on, but then it stays in the vacuum before jumping abruptly. And in green is the average of multiple trajectories. And on the right side of the B-stability region, we expect to see something similar, but now for the bright phase. So we can perform the same experiment, but this time we initialize the system and the bright phase, and we turn the pump off at t is equal to 0. The system remains in the bright phase for a certain time, even though there's no pump, and then it jumps in the vacuum abruptly. And again, we can average over multiple trajectories, and we obtain this orange curve. We can also take the number of photons after a time corresponding to the lifetime of the cavity and get the global picture of these metastable states in the same schematic. From these two curves, we can also extract the characteristic lifetime of our metastable state. So we simply fit exponentials. And then to get the global picture, we can do this for all values of the tuning and for different values of pump amplitude. And this is what we get. So here, I plot this coefficient of the exponential for the different detuning. And as we increase, the scaling parameter L. So what we see is that we have a minimum, which coincides exactly at the position of this first order DPT. And we have that this minimum becomes lower and lower as we go towards the thermodynamic limit, which is a clear signature of critical slowing down, meaning that our state lives longer and longer. So for the second order DPT, what does the model predict? So this is the other region. It predicts that we should have a squeeze state exactly at the critical point, that we should again have some critical slowing down, but this time it's the rate at which the state goes from alpha to minus alpha that becomes slower. And we should have spontaneous symmetry breaking. That is that when we're in the true thermodynamic limit, this rate is so slow that we only see one of the alpha states. So again, we went and looked at the measurement. So this is the photon number as a function of the detuning close to the second order transition. And if we take the second derivative of this, we have a peak, which should coincide with this transition. And we can look at the squeezing as a function of the detuning. And we see that this peak, which corresponds to the second order phase transition, coincides exactly with the minimum of the squeezing. So we have squeezing at the critical point below vacuum. Now for the critical slowing down, what we take are time traces at different values of the tuning, like this. And we look at the time that it takes to go from alpha to minus alpha. So here notice that the X scale increases by a factor of 10 each time. So we have that as we move away from the point of the transition, it takes a longer time to go from alpha to minus alpha. And we can actually extract this time by taking the trajectory and calculating the autocorrelation function, which is shown here, and again fitting these functions with some exponential. So the coefficient of the exponential gives us information about this switching rate from alpha to minus alpha. And we do just like before, we redo this measurement for all values of the tuning and for different values of our scaling parameters. And we see kind of a similar behavior. So as we increase the scaling parameter, as we bring the system more and more towards the thermodynamic limit, we have that this rate becomes slower. And it also becomes slower as we move away from the transition. So as a summary, we've managed to build a model that describes both the first and the second order dissipative phase transition in our system, and we have observed all of the key characteristics of this model. And now with this better understanding of DPTs and the model that we found, we believe that we're ready to try to pursue some real applications. Thank you.